This is Dan Olds on behalf of Hyperion Research and Inside HPC, and we are interviewing David Martin today from Argonne National Lab. How you doing today, David?
I'm good. How are you?
I'm okay. And this is going to be interesting. I'm looking forward to hearing what you have to say. So let's start with some basics. How did you get involved in HPC?
Yeah, so my background really is out of computer networking. And so, the dirty secret for HPC and especially high-end supercomputers is it's really a network. I mean, the processors are a lot of times commodity processors, but the secret sauce is the network. And so,
as some say it's a dark art.
It is a bit. I mean, but I actually started at Bell Labs after college and did packet communications at the time when packet communications in Bell Labs was a strange thing. They believed that everything should be circuit switched. And so we were a ragtag group pushing packet switching and got me really hooked on the bug of making networks as fast and as interoperable and as performative as possible.
So would you kind of summarize your HPC career by saying that you are a network-based practitioner?
I guess so, yeah. I mean, I after Bell Labs, I moved to Fermilab and I ran wide area networks for quite a while. And then I went to IBM and they were just getting into the internet, which seemed strange at the time, but at the time they didn't have much of an internet business or presence at all. And they were looking for people who knew TCP/IP and knew how to build networks. And so I did that. And then, networking then led me into computing, which is kind of how I got into grid computing. So I did some grid computing when I was at Fermilab. A lot of it was going on then at IBM because they really saw networking as the way that they could tie together all their big computing centers, which up until the time had been pretty much islands. Even within computing centers, all the machines were islands, and they wanted to start becoming more of an internet company and hooking those together. And so that kind of led me to HPC in kind of a roundabout way.
Okay. What are some of the biggest changes that you've seen in HPC over your career?
Well, going back to the days when I was at Bell Labs, I had one of the first Sun Microsystems workstations on my desk. And mostly the reason I had it is because nobody else kind of really could figure it out because they were still using a lot of mini computer or mainframe based computing. And this thing,
a lot of terminals and things like that.
Yeah, exactly.
Terminals. Yeah.
So, the group that I was part of at Bell Labs there started using them. And then when I got to Fermilab, the boss that I had there was into distributed computing. And I think the motto for Sun for a long time was the network is the computer.
Yes. I was actually with Sun during those glory days. Yes.
Oh, interesting. Oh, it was fun. Yeah. I mean, it was a small enough company that, when I found bugs, I would call the engineer that wrote the code. Yeah. You don't get to do that much anymore.
No, you don't. Very interesting stuff.
No, to just kind of finish the question about the changes I've seen. I mean, I think it's taken a long time for those changes to propagate through the whole computing sphere. And so that was something that it was big among, people who are using Sun Microsystems stuff, but it took a while. And if you look at a lot of the cloud computing now, again, the network is the computer, and the ability of cloud providers to provide all this raw computing power is really dependent upon having networks that work and are reliable and interoperable and all. And so I think that kind of distribution through kind of the whole computing ecosystem is the big change. And that and the fact that now people are really having to do parallel programming. I mean, you could get away for a really long time about single-threaded code and ignoring the fact that there are multiple nodes and all. And you can't get away with that now. Even if you're programming for your, laptop PC, you have, 16 cores or something in it now. So.
And if you program for single thread, your performance is just going to go down over time.
Right. Well, yeah, even in the supercomputers now, the core counts and clock rates are not going up a huge amount, right? So it's all about being able to take advantage of parallelism. So.
Yes, exactly.
Yeah.
So where do you see HPC headed in the future? Are there any trends that excite you or have you concerned?
Well, I mean, the introduction of accelerated computing and GPUs, I think is both exciting and concerning.
Mm.
It's exciting to have that much access to just raw computing power. I mean, we haven't been able to have a step change like that in quite a while. I mean, we've been limping along with, trying to even hang on to Moore's law, and the ability to stick, a whole bunch of GPUs in a machine. The Aurora system that's coming to Argonne next year.
Yes.
I mean, will be, most of the computing power will be in the GPUs, and so, having an exascale level of computing power is really exciting. The challenge, I think, is what it'll mean for the codes that are out there now. Refactoring all those codes is non-trivial.
Yes.
I'm involved a bit in the exascale computing project. And it's a huge effort to refactor a lot of codes that are important to the Department of Energy and the kind of general scientific community and make them work in an exascale environment. But that's a lot of work. And so it's exciting and it's interesting, but I'm worried somewhat about, all of the accumulated HPC code that's around and maybe not working great in the GPU environment. So
that is going to take a lot of time and effort and expense, but at least I think we're fairly certain that GPUs are going to be around, so you're not doing it for nothing.
I hope so. Yeah, right. all that work for nothing would not be good. And the other trend that I see that I think will probably help some with that is coming from the cloud world, which is the whole virtualization and being able to do things like Docker and Shifter and Kubernetes and all. You haven't seen those too much in the HPC environment, but they're starting to go in there. And I think the next generation of supercomputers will kind of natively support that, and that'll help a lot. So maybe people won't necessarily have to rewrite every application for every piece of hardware the way that they do now in HPC. If you have virtual machines, most of the rest of the computing world has been willing to trade off performance for programmability.
Yes.
So if a lot of programs aren't maybe that efficient, but they're portable and you can run them on all kinds of different hardware. HPC has always been about squeezing the last ounce of computing out of a piece of hardware and getting everything out of the way. And I think the computing power is starting to be there where you can not really have to worry about that so much.
Yeah, there's always been a worry with virtualization about the overhead of it.
It's true. Yeah, I mean there is overhead. But even if you look at traditional HPC applications, a lot of them don't run at the raw computing power that is there anyway.
True.
True. Some do, and some people pride themselves in the fact that they're getting 70 or 80% out of
theoretical. Yeah, and it's going to be interesting. I think that when we get into the low single digits of overhead, that'll mark sort of the sea change towards virtualization.
Yeah. And like in the cloud, it's probably there'll just be so much raw computing power that it'll be worth the trade-off.
Yeah, I think that makes sense.
Yeah.
Is there anything else you want to say that we didn't cover that I should have asked?
Well, I mean, I think the challenge in high performance computing is especially as cloud comes along and there's more and more capabilities in commercial offerings, is for high performance computing to make the systems usable in a wide variety of applications and environments and people. Being at it, we were joking at the very beginning that the large HPC centers look down on other people, and it's kind of a joke. But the reason for that perception is that a lot of these systems are just fiendishly hard to use. And so it requires a cadre of people who have spent years building it and designing it and understanding it. And so I think the challenge for the high performance computing community in general is to open that up and make it so that a lot of people can make use of it. And I think the emergence of the exascale systems will help that some, because the design of them will be much more open, where we'll be able to do data analysis and artificial intelligence and traditional simulation all kind of simultaneously.
You have a fair amount of capacity then.
Yes. Yeah, that we can stop it up. You know, we've never run into a situation where we've got a new machine and we don't know what to do with it. So
yes, and that's always something that when I was on the vendor side, we would come out with bigger machines and people say, well, it doesn't need to be that big. Yeah, it does. It'll get used.
Yeah. No, I mean, we've already got projects that, you know, basically are asking for the whole Aurora system. And, you know, it's not even, you know, pieces haven't even started showing up yet. We're a year away from even seeing hardware.
But they're already pitching you on using the whole thing.
They're already pitching on why these projects need that amount of time. So.
Oh, wow. Well, look forward to hearing in the future what those projects were, because that's a lot of capacity to use.
Yeah, well, you know, if you look at a lot of the traditional ones, astrophysics or climate or anything, you just shrink your grid a little bit or
adds more variables and it starts really ramping up.
Yeah. It's easy to get exponential growth in computing power as well. And, you know, some of the really creative things that they're doing will actually require it. It's not just that they're trying to fill it. So.
Well, great. Well, thank you so much for the time. This has been really good.
Yeah.
Really appreciate it. And on behalf of Hyperion Research and Inside HPC, thank you all for watching, and we'll talk to you again soon.